All right, here we are, everyone, for the Set 1 E and M free response questions for AP Physics C Mechanics 2022. This one is going to be kind of interesting. There are some questions that seem a little bit kind of easier, a few that seem a little bit more difficult. And so I haven't gone through all of these, and so this is going to be quite the experience for us. But let's go ahead and get started. So first off, you do have a non-conducting sphere. That's the very inner part, the very inner gray part. And then you do have a thin concentric conducting spherical shell. So that is the outer gray part as well. The sphere has a charge of negative Q and the shell has a charge of plus 3Q. And we're given the radii. And we want to determine the charge on the outer surface of the shell. And thinking about that, I can actually go ahead and say that that charge is going to be equal to plus 2Q. Now, the reason that I can say that that is going to be true is actually because of Gauss's law. That outer thin ring is actually going to have zero electric field in electrostatic equilibrium. And so therefore the inner surface of the shell has to have plus Q in order to cancel the negative Q for the non-conducting sphere. Therefore, if I create a Gaussian surface inside that thin conducting spherical shell, the enclosed charge is actually going to be equal to 0 then. And therefore, the outer part of the conducting shell gets the remainder of that excess charge. So for part B, then, essentially what we have to do is we have to use Gauss's law to derive an expression for the electric field when little r, that is less than big R. So if you remember, that part of the system is a non-conducting sphere. So it is not true that the electric field is equal to 0. If this was a conducting sphere, the electric field would be equal to 0. However, in this case, we do actually have to use Gauss's law. So we have integral of E dot dA is equal to enclosed charge over epsilon naught. But do note that the enclosed charge itself is going to be equal to the charge density, which is uniform, times the enclosed volume by a Gaussian surface. We're going to go ahead and use a Gaussian sphere of radius r. Gaussian sphere radius is equal to little r. Now, the charge density, because this is a uniformly charged non-conducting object, is just going to be total charge over total volume. And so therefore, it's just going to be negative Q over 4/3 pi big R cubed. And so therefore, what we can do is we can actually go ahead and just simplify the integral to E times A. The electric field is going to be constant and normal to all parts of our Gaussian sphere. And so we have E times the surface area of our Gaussian sphere is going to be equal to charge density, which is going to be Q over 4/3 pi big R cubed. And then enclosed volume will be 4/3 pi little r cubed. And all of that should be over epsilon naught. And so there should be a negative sign here. Do keep in mind that the non-conducting sphere is negatively charged. And so if I go ahead and simplify this down, using A is 4 pi little r squared, and I'm actually running out of room here. I do apologize. I do get that the electric field is going to be equal to, in terms of magnitude, Q little r over 4 pi epsilon naught big R cubed. And it should be pointed to the center of the sphere. And I am going to include that in my answer. This question is not asking about the magnitude of the electric field, it is just saying an expression for the electric field. So I can either write this expression, say, to the center of the sphere, or I can put a negative sign. That negative sign is going to indicate that the electric field is actually pointed to the center of the sphere. So I can either have the negative sign or I can have the words to back it up. Part C says that the field at little r is equal to big R is 8 newtons per coulomb, calculated when r is equal to 2 big R. And so if I go back one page, 2r is actually in between the two grade parts. And so if I go ahead and apply Gauss's law, well, that inner part is going to look like a point charge. So the electric field is going to be proportional to 1 over little r squared. Therefore, if I double the radius, I get an electric field of 2 newtons per coulomb. Just a proportionality right there. All right, determine an expression for the absolute value of the potential difference between the outer surface of the sphere and the inner surface of the shell. So that's going to be when we are in that empty space again, and express in terms of Q, big R, and physical constants as appropriate. And so what this is actually going to be, this is a potential difference between, again, the outer surface of the sphere, which is at big R, and the inner surface of the shell, which is at 4r. And it's going to be E dotted with dr. Now, the thing to note is that the electric field is going to go like negative Q over 4 pi epsilon naught little r squared dr from big R to 4 big R. That negative sign again is present because the non-conducting sphere is negative charged. So the way I got this formula, and I should actually probably go back and show my work a little bit more in part C, is because I applied Gauss's law using a Gaussian sphere that is now at little r is greater than big R. So EA is equal to Q enclosed over epsilon naught, which is negative big Q over epsilon naught. A is 4 pi little r squared. So I should include that for part C, just to be clear on how I determine that E is proportional to 1 over little r squared then. So I would probably need to put that remainder part of the work for full credit there. Okay, going back to part D though, I can go ahead and integrate this out. I do get negative Q over 4 pi epsilon naught little r, and that's from 4r to big R down there as well. So this is going to be negative Q over 16 pi epsilon naught big R plus Q over 4 pi epsilon naught big R. And that is going to be 3Q over 16 pi epsilon naught big R. And do note that this is a positive number. It does ask us for the absolute value of potential difference. And so therefore, this is going to be my final answer. So for part E right here, we are asked to draw a sketch of the electric field as a function of distance. And so essentially what I need to do with this is I do need to actually take into account my answers to part B and part C. In part B, I determined that for little r less than big R, electric field was proportional to just R. Also, it was negative because we had a negative charge. And then part C, I determined it was proportional to 1 over r squared, again, negative. Now, when I go outside of that conducting sphere, it's actually going to change to be positive because now the enclosed charge is positive. And so I should expect to see a linear function for the first region, a negative 1 over r squared for the second region, and then finally a jump because that conducting spherical shell is very thin. Finally, then a jump and another 1 over r squared. So that would be how my electric field looks. Now, for the electric potential, we need to note that electric potential is essentially negative integral of electric field with respect to r. So if I have a 1 over r squared outside, I should have a 1 over r. So a 1 over r, and I apologize, this is actually very difficult to draw. Let me redo my region 3 for the electric field. It should actually decrease quite a bit faster. And that'll leave me a little bit more leeway with my electric potential, which doesn't decrease as fast because it's not a 1 over r squared, but rather a 1 over r. Now, for the second region, do note that I do have 1 over r squared as well. So I would expect the general trend to be negative 1 over r in region number 2 for the electric potential. So negative 1 over r is going to look very similar. again, it just doesn't drop off as fast as the electric field would. So it should look something along the lines of this. Now, finally, in that last region, because I have negative r, I would expect to see something along the lines of r squared then, because if I take negative integral of negative r, right, electric field goes like just negative r. So negative integral negative r would just be r squared over 2 approximately, with respect to r, of course. And the reason why I would say that that does make sense is because the positive charge isn't just going to want to stop at the very surface. Now, if I think about if I have a uniformly charged positive conducting sphere, what's going to happen? Well, what's going to happen is I would expect that if I place a positive charge right here, right, some other positive charge right here, it would end up going out like this. So likewise, what I should expect is I should expect that if I place a positive charge inside a negative insulating sphere, it goes to the very center of that. So I think that I should expect to see something along the lines of this. So again, this would be something like negative 1 over r. This would be positive r squared. This would be positive 1 over r then. And I do apologize, my drawings are very, very poor. However, hopefully having those trends present will kind of help you in terms of deciphering my drawing there. And that is it for question number 1 then. So let's go ahead and move on to question number 2. We now want to study the potential difference across a capacitor as it discharges across a resistor. We have to go ahead and draw a circuit for it. And so essentially what I need to do is go ahead and create that circuit. Now I can use multiple switches, but I can only use one of everything else. So here's how I am going to design my circuit. I am going to actually have 2 switches. I am going to have an empty branch with just a switch. That might seem unnecessary, but I'm going to explain why in just a minute. And then I'm going to go ahead and have my resistor, and then I will go ahead and have my variable capacitor then. And then in addition to that, because I want to study the voltage across the capacitor, I should go ahead and put the voltmeter in parallel with the capacitor. All right, now the reason why I've designed my circuit such as this is because if I close that top switch, I can charge the capacitor. And then after that, I can open the top switch and actually close the switch in the middle branch. And then I can go ahead and discharge the capacitor without worrying about the battery. So I think that this is probably the best setup you could use. There are other possible setups that you could use in terms of how you would want to lay out your switches. This is the one that maybe makes the most sense to me. But if you have a slight variation of it, then you're probably all good to go. Now for part B, we are asked to show the equation for the potential difference across the capacitor as it discharges. How do we get an exponential? We have to actually write and solve a differential equation. So when the capacitor is discharging, the voltage across the capacitor plus the voltage across the resistor should be equal to 0 by Kirchhoff's loop rule. And so what that's going to look like is that's going to look like the charge on the capacitor divided by capacitance. That comes from C is equal to Q over V. So I solve that for V. And then I'm going to have plus the current, which is dq dt, right? Current is the derivative of charge with respect to time multiplied by R. So Ohm's law is equal to 0. Therefore, dq dt is negative Q over RC. And in terms of how that's going to look, I do have to apply separation of variables. So dq over q is equal to negative dt over RC. So if I go ahead and integrate both sides, I get ln of charge is equal to negative t over RC plus an integration constant. Therefore, I get that charge as a function of time is a e to the negative t over RC. But again, noting that voltage is equal to charge over capacitance, I end up getting that voltage is equal to a constant times e to the negative t over RC. Now do note that the initial voltage in discharging is equal to the battery voltage. So therefore A is going to equal delta V naught. And so therefore delta V C of T, the voltage across the capacitor, the potential difference across the capacitor, right? V and delta V, I'm kind of using them interchangeably. They do represent the same thing in my notation. And that's going to equal delta V naught e to the negative T over RC then. And so the solution is shown. All right, so part C then gives us another graphing question. We are now asked to go ahead and draw a best fit line. Just like with the mechanics one I did on my tablet, I am going to just go ahead and do an auto best fit line here. It's not entirely automatic. I have to still draw the line, but it means I don't have to try to carefully get a straight line just by free-forming it on my tablet. Okay, and so we drew the best fit line. Now we have to determine the unknown capacitance. Now the thing to note is that if I take my equation, the one that I have to show in part B, I can go ahead and make it look similar to what I have on the graph. So I get delta VC over delta V naught is equal to e to the negative T over RC. Therefore, natural log of delta VC over delta V naught equals negative T over RC. And so that should tell me that the slope is equal to negative 1 over RC then, or therefore C is negative 1 over R times the slope. So what is the slope here? Well, that's going to be a little bit difficult for me to do right here, but I'm going to do my best. Let me go ahead and actually switch colors once more. All right, there's my first point that I would like to use. And here is my second point. So what points are those? Well, let's go ahead and switch back to the correct color. Those points are going to be, it looks like 0.1 comma, let's see, 1, 2, 3, 4, 5, negative 0.12. And then the second point is 0.16 comma, negative 0.2. And so my slope is going to equal negative 0.2 minus plus 0.12, negative minus a negative sign, of course, over 0.06. And if I go ahead and I put that into my calculator, what I am going to get is 0.08 on the top. Of course, that will be negative, so I'll make sure to put that in my work. I do get a slope of negative 1.33 in my graph. And so going ahead and plugging that in, then I will find that the capacitance, I do have to divide by 150,000. Make sure that you change that kilo ohms to ohms for those SI units. And then I divide it by the slope, 1.33. I am going to get a value for capacitance of, let's see, it looks like 5 microfarads. So 5 microfarads is the capacitance that I have determined then using my slope. So I use that formula, C is equal to negative 1 over R times the slope to get that. All right. So going ahead and moving on to the next part, part D says that the capacitance is adjusted so that the surface area is increased. Would you expect the slope to be more steep, less steep, or unchanged? Well, going back to our equation, I'm going to go ahead and reproduce it before I forget it. C was equal to negative 1 over R times the slope. So if I increase the plate area, so plate area increases, that's going to mean that capacitance increases because C is equal to epsilon naught A over D for parallel plates. Therefore, if C increases, what I would expect is that the slope being proportional to 1 over C is going to decrease then. So in that case, I am going to expect to see a slope that is actually less steep. All right, so taking a look at part E now, would the slope and would the vertical intercept of the graph change if the battery has internal resistance? Well, let us go ahead and look back at the graph right here. And let's take a look at exactly what having internal resistance means. So having internal resistance does mean that V naught is going to change. Delta V naught is going to change. The voltage supplied to the capacitor is going to change. It will no longer actually be delta V naught. It will be something a little bit smaller than that. Now, in terms of VC, delta VC, that is going to be changing as well. Now, what would I expect? Well, I would actually expect that I would see that both of those would change by the same amount, right? If V naught changes a little bit, then you're going to get that delta VC is also going to change by that same amount, right? If I cut delta V naught in half, if the capacitor only gets half the voltage that would have for an ideal battery, that's going to start with half the voltage, but it should still decrease at the same rate. Now, so going back to the question, I would actually say that the slope is not changing. And again, the reason why is that delta V naught and delta VC, delta V naught, let's just start with that, changes. This means that, delta V naught is no longer, let me be a little bit more clear with that. Delta V naught is no longer the voltage supply across the capacitor. Instead, it is less than V naught. However, I'm not really happy with how I'm wording this. I do apologize. This is my first time actually taking a look at this question itself. So I'm kind of trying to figure it out as I go. And part of the reason I'd like to do that is so you can kind of see my thought process. However, delta VC is still going to change at the same rate, to drop at the same rate, because the battery is not in the closed loop during discharging. Now, would the vertical intercept change? I do believe that would, because if I take a look at the vertical intercept, that represents this quantity when t is equal to 0, right? Delta VC when t is equal to 0. So if delta VC at time t is equal to 0 is now less than delta V naught, then you no longer have ln of 1 as you do for an ideal battery. Ln of 1, of course, is 0, but ln of something less than 1 is going to be a negative number. Therefore, the vertical intercept is going to change. And I'm feeling pretty confident about both of those. So regarding question number 3, we now have a light bulb and it's connected, and you have a rectangle loop and a very long current carrying wire. And this is very clearly going to be something that is based on electromagnetism because you have a varying current here. So the first thing that we have is, what is the direction, if any, of the magnetic field produced by the induced current as the current in the long wire changes direction? So this means that you do have current initially flowing to the right. So I is initially flowing to the right. As time goes on, the change in current in the wire is actually to the left. So the question is, what does that mean about the change in magnetic field then? Well, with current going to the right-hand rule is going to imply, so with current initially flowing to the right-hand rule is going to imply that the magnetic field is pointed out of the page. Now, as that current decreases, what you are going to get is you are going to get that magnetic field starts to decrease as well. And so therefore, the change in magnetic field is actually going to be into the page. And so therefore, the induced current should counteract it. Lenz's law says the induced current is directed to counteract the change in flux. Now, the answer is not no direction because the field is zero, because induced current doesn't care what the field is. It cares about how the field is changing. So there we go. All right. Calculate the magnetic field through the loop due to only the long wire at time t is equal to 3 seconds. So at t is equal to 3 seconds, we do have that the current is actually going to be given by, let's see, 10 minus 2 times 3, which is going to be equal to 4 amps. Now, it's a very common result, and I would recommend maybe rederiving it via Ampere's law. But the magnetic field around a thin wire, a very long current carrying wire, is proportional to 1 over R. So Ampere's law, let's just go ahead and prove it, is going to be equal to B times 2 pi R. So I can use an Amperian circular loop. Is going to equal mu naught times I. Therefore, B is equal to mu naught I over 2 pi R. Now, keep in mind that that field is not constant actually throughout the entire loop. That field is actually decreasing as you get higher and higher up in the picture. And so the magnetic flux is actually not going to be something that we can necessarily just pull out of the integral right away. We are going to need to do a little bit of simplification here. So the thing to note is that the change in area, while the magnetic field doesn't change along the length, so dA, I can go ahead and actually pull out the length, and then I have integral of mu naught I over 2 pi R with respect to R. How big is R? Well, it's going to be from 1 to 3 centimeters, so 0.01 to 0.03. The way I know that is because the lower edge of the rectangle is at 1 centimeter, the higher edge is at 3 centimeters right there. So integrating that, I get mu naught IL over 2 pi natural log of 3. And how do I get natural log of 3? Integral of 1 over R is natural log, and the subtraction of natural logs is their division. So ln of 0.03 over ln of 0.01 is going to be ln of 0.03 over ln of 0.01, which is just 3. So yeah, I do actually need a calculator for this as well. Probably one more powerful than what I have present. I think what I'm actually going to do is go ahead and maybe comment down what my answer is for this one, because I don't want to take the time to actually go ahead and search for my graphing calculator right now. And my 4-function calculator, or even my scientific one on my phone, is probably going to be a little bit tricky to work with. So what we have is calculate the current through the light bulb at t is equal to 3 seconds. So the thing to actually note is that we do need to actually calculate the current, and that's going to be equal. That's going to be just induced current, and so that is going to be equal to the induced EMF over the resistance. Well, how do we get induced EMF? Well, we have to actually take the negative derivative of flux over with respect to time then. So we do actually have to get an equation for the change in flux in terms of time, but that should actually be fairly easy, because in part B, we showed that we can do mu naught IL over 2 pi R ln of 3. This was our flux at time t is equal to 3. Now, something that you'll notice is that this entire thing does have some time dependence, and that is actually in the current. So I can go ahead and write this out. I'm going to get mu naught C minus dt, excuse me, capital D times L over 2 pi R ln of 3. Now, if I take the derivative of that with respect to time, the C goes away and I'm only left with negative D. So it's negative mu naught DL over 2 pi r. Sorry, there's no r here. What am I doing? There's no r there. We integrated and got rid of the r, and there shouldn't be an r there. I do apologize about that. Yeah, so this is our derivative then, with a flux with respect to time. And then I just have to divide that by the resistance. So the induced current is going to be negative in terms of the numbers 4 pi times 10 to the negative 7th. I do have to go back and double check what everything is. D is 2 and R is 10. So times 2 times 0.04 for the length, 2 pi times 10 for the resistance, ln of 3. And that is going to get me my numerical answer for the induced current. All right, group of students try to attempt whether the current is correct. The current is measured to be greater than the current that was actually calculated. Which of the following could explain the discrepancy? And so the things that I do want to take a look at, let's see. So the student did not account for the Earth's magnetic field. That would likely not contribute. That would not be correct. And the reason why is because the Earth's magnetic field is constant. So it's not going to cause any change in flux. It'll only change the flux by a constant value at every single point in time. Therefore, it doesn't matter. The rectangular plane is tilted. Again, that's probably not going to be too much of an issue. The resistance is greater. That wouldn't cause the current to be greater. Absolutely not. The long side is shorter than the recorded value. No. And in fact, the only one that does make sense is the last one. And that does actually make sense because if the current changes at a faster rate, right, current changing faster implies a faster change in flux, or a higher rate, a higher derivative, higher rate of change of flux, therefore larger induced current. There we go. So you can either use process of elimination, you'll arrive at the correct answer, or you can just look at the answer choices and select the best one. You know, it's a lot to read through, so I figured I'd just go through and eliminate them all one by one. All right, later the same rectangular loop is rotated such that the short side is 1 centimeter above the current carrying wire, and you have the same current, and you want to figure out at time t is equal to 3 seconds, is the current in the light bulb larger or smaller? So going back to that equation that I have in part C, right? C says that current is going to be proportional. Well, what's actually changing? The length is changing. And also something else that is changing is that natural log, L times ln of the change in width, essentially plus 0.01. Actually, sorry, ln of, you know, I'm trying to think of a good way to actually notate this. Let's call this like bottom and top, right? Bottom and top. So top plus 0.01 over bottom plus 0.01. Actually, bottom is just located 0.01 away. So something along the lines of this. Okay, and so what's actually happening? Well, the length is going down, and then the ln is actually going to rise. However, natural log rises slower than the length, right? The length is actually from left to right, and the ln, the natural log, depends on going from bottom to top then overall. It's the ratio of the positions of the bottom and the top to the bottom from the long current carrying wire. But ln always rises slower than a linear change. So it always rises slower than big L goes down. And therefore, I would expect the current to actually be lower in this case then as well. All right, so that is free response question set number 1 for E&M for the 2022 AP Physics C exam. I hope that you learned something from this. If you do have any questions, do feel free to comment down below. I know that I was kind of maybe a little bit rushing through this last part right here. Hopefully it still kind of made sense. Again, I was trying to think through it as I was actually solving this this question as well too, but I'll be happy to answer any other questions that you have. As usual, thanks for watching. I hope that you learned something, and I'll see you later for set number 2 for the E and M free response questions. Take care, everyone.